At their core, computers are nothing more than billions of tiny switches turning on and off millions of times per second. Yet from this simple foundation emerges everything from video games to artificial intelligence. Understanding how this happens requires building up from absolute basics. Everything in a computer begins with electricity, specifically the presence or absence of electrical voltage. When voltage is present, we call this state 1. When voltage is absent, we call it 0. This is binary, the fundamental language of all digital computers. Every piece of information, every calculation, every image and sound ultimately reduces to patterns of ones and zeros. The physical component that creates these ones and zeros is called a transistor. A transistor is an electronic switch that can be turned on or off by applying voltage to it. When a small voltage is applied to the control part of a transistor, it allows current to flow through, creating a 1. When no voltage is applied, no current flows, creating a 0. Modern processors contain billions of these transistors, each smaller than a virus. Individual transistors become useful when combined into structures called logic gates. A logic gate takes one or more binary inputs and produces a binary output according to a specific rule. An AND gate outputs 1 only if both its inputs are 1. An OR gate outputs 1 if either input is 1. A NOT gate simply flips its input, turning 1 into 0 and 0 into 1. These simple gates can be combined to perform arithmetic. An arrangement of gates called a half adder can add 2 binary digits together. Multiple half adders combine into a full adder, which handles carrying digits just like adding in base 10. Chain enough of these together, and you have a circuit capable of adding any 2 numbers. Similar arrangements enable subtraction, multiplication, and division. Computers also need memory to store information. The simplest form of memory is called a latch, built from logic gates arranged in a loop. This circuit can hold a single bit, maintaining its state of 1 or 0 even after the input changes. By organizing millions of these latches together, you create random access memory, where each bit can be read or written independently. The central processing unit orchestrates everything. At its heart, the CPU contains an arithmetic logic unit built from the gates we discussed, registers made of latches to hold data temporarily, and a control unit that coordinates operations. The CPU follows instructions stored in memory, each instruction represented as a specific pattern of ones and zeros. When you run a program, the CPU reads the first instruction from memory. This instruction might tell the CPU to load a number from a specific memory address into a register. The next instruction might add another number to it. A third instruction might store the result back to memory. The CPU executes billions of these simple instructions every second, and from this emerges complex behavior. Higher-level programming languages provide a more human-readable way to write instructions. When you write code in a language like Python or Java, a compiler or interpreter translates your commands into the binary instructions the CPU understands. A single line of code might become dozens or hundreds of machine instructions. The screen you see, the keyboard you type on, and the storage that holds your files all connect to this same system. Each device has specialized circuits that translate between the physical world and binary signals. When you press a key, a circuit converts that physical action into a binary code representing which key was pressed. When the computer wants to display something, it sends binary data to the graphics processor, which converts it into voltage levels that control millions of tiny colored lights on your screen. What makes modern computers powerful is not any single clever component, but the sheer scale of integration. A smartphone processor contains over 10 billion transistors, each switching states billions of times per second. This massive parallelism, combined with sophisticated architectures that predict and optimize instruction execution, creates the illusion of a machine that thinks. The remarkable truth is that there is no magic happening inside a computer. Every operation, no matter how complex it appears, breaks down into electricity flowing through carefully arranged switches. The computer does not understand the video it plays or the document it displays. It simply manipulates patterns of voltage according to rigid rules, and we have learned to encode meaning into those patterns. From switches to software, from transistors to artificial intelligence, Everything rests on the foundation of ones and zeros, flowing through silicon.